Okay, we're going to get started then. Welcome to today's Royal Meteorological Society's Weather and Climate webinar. Today we're focusing on stochastic event sets, which are a critical tool used in risk assessment within the insurance industry. My name's Conor Lamb. I'll be hosting today's webinar, and I'm the Royal Meteorological Society's Science Engagement Fellow for Insurance. So before we get started, just going to give a little bit about the Royal Meteorological Society, or RMETS. So we're the world-leading learned society for weather and climate scientists and sciences with over 3,000 members. The society was founded in 1850 and recently had its 175-year anniversary. Over the 175 years, the society has changed quite significantly. However, it still aims to promote the advancement and extension of meteorological sciences. So there are a lot of benefits on the screen that you can look at, and we'll move on, I suppose. So today we've got a really great webinar on stochastic event sets. Just a little bit of housekeeping, I suppose. So we're going to hear from our three speakers, and then at the end we'll have about 20 minutes for Q&A. If you could please put questions in the Q&A tab on Zoom, that'd be great, and we'll pick them up from there. Great. So our first speaker is Alex Doyle. Alex did his undergrad and PhD at the University of Reading in atmospheric sciences and meteorology, and is now at Verisk as a model product manager. So I'll stop sharing my screen, and Alex, you should be able to go.
Thanks, Connor, for the introduction, and hello, everyone. I'll just get set up here. All right, hopefully you can see that on your end, Connor. Fantastic. Okay, so yeah, hello, welcome, and it's a privilege to have the opportunity today to talk to you all about stochastic event sets in the context of catastrophe modeling. So you'll notice I mentioned catastrophe models quite a lot during this presentation, and that's because, you know, the stochastic event sets that we're going to be talking about, they are what underpin these important catastrophe models. Perhaps you're familiar with them and have worked with them before, or maybe you've never come across them until today. But either way, there'll hopefully be learnings in here for everyone. So let's jump in. So in the next 15 to 20 minutes or so, we are going to cover some of the crucial questions when it comes to CAT models and the stochastic event sets that underpin them. So to start with, why build catastrophe models in the first place? What actually are stochastic event sets with respect to catastrophe modeling? A quick case study from how we at Verisk have developed and continue to develop catalogs of stochastic event sets. And we will finish with an overview of the surprising number of ways that these stochastic event sets and the catastrophe models that use them can be and are used. So deep breath and let's dive in. So before we delve into the what of stochastic event sets, we need to start by asking the question, why build the catastrophe models that they're so important for in the first place? And a bit of a spoiler alert, the very short answer is on this slide, but there's a little bit more to it than that. Now, historical records vary greatly depending on the peril. But generally, we don't have a lot of confidence in a spatially complete view of risk until post-satellite era, around 1979 and afterwards. Some perils, like hurricanes, are our best case scenario. You know, we almost have a century of reports from for this peril. But for some other perils, such as severe thunderstorm, for example, we have numerous reports, but there's significant spatial and temporal biases to overcome even to this day. And, you know, robust records go back a few decades at most, despite there being numerous in number. Now, reanalysis data, another really crucial source of data, both in many academic circles, but also in catastrophe modeling, also has its issues. As you can see in this figure, reanalysis data, essentially our best estimate of the historical atmospheric conditions, is poorly constrained the further back in time you go. It essentially relies on a few set of observations in a model if you go back far enough. And those of you who know your atmospheric science might know that even today, we know there exist many biases with pre-analysis data. So why is all of this important? Why am I telling you all this? Well, it means we don't have a complete understanding of what might occur today. Essentially, we may not have seen every possible storm or flood in our historical record that could possibly occur. So history isn't long enough. But secondly, the history that does exist can be biased in many ways. So this is part of why we build catastrophe models and why the stochastic event sets that underpin them are so important. The focus of catastrophe models is to determine the near present risk. Essentially, what might happen today or next year or the year after that. It's not so much a weather forecast as a view of the risk over a longer period of time. So these CAT models need to work out if the historical records that I've talked about here are reflective of today. And you might think there's natural or artificial reasons that could be at play here, and you'd be absolutely right. There's climate change or there's population increases, respectively, that might be involved. How can we disentangle those different effects? Well, that's where CAT models come in. They try to answer these questions and are grounded in the latest science in order to provide a latest view of risk. So we can think about this problem a little bit further by considering the idea of counterfactuals. That is to say that essentially every storm is just one version of what could have possibly happened. A counterfactual is to consider an alternate possibility for a storm, for example. So some of you may remember Storm Ciarán in 2023 and pictured here with its synoptic chart as it's moving over the UK into parts of France and Belgium. Now, the loss picture that we saw from this storm in terms of insured losses are shown by the reds and darker reds in this picture. So the biggest losses, the most amount of claims, came from areas around France, northeast France, into Belgium, and also the Channel Islands associated with this storm. But what if Storm Ciarán here had actually veered 50 kilometers further north? You know, the loss picture that we see here that I've just described could look very different. Jersey and the Channel Islands might not have got its tornado that you may have heard about, but it might have hit densely populated parts of southeast and London instead. So just because we haven't seen it this time, it doesn't mean it hasn't happened or couldn't happen in the future. And this simple what if question is at the heart of catastrophe modeling and stochastic event sets, as we are soon about to see in a little more detail. And note that stochastic event sets do usually go much further than simple counterfactuals. I'll give an example a bit later, but it's often a good starting point when thinking about what could occur in the future. Additionally, the insurers, the actual users of these catastrophe models, must understand their risk from one or more perils across large and complex portfolios, consisting of houses, businesses, cars, and more. These portfolios can be global in coverage, essentially wherever there is an insurance market. Therefore, Verisk builds a multitude of models for a large number of countries and regions, as you can see in white in this figure. And you can have a bit of fun looking at each of these logos at the bottom and trying to guess which peril or hazard they are referring to. Okay, so now we know a little bit about the why. So next, let's consider the what in a bit more detail and focus in on these stochastic event sets. Notice I use the word art deliberately here because catastrophe modeling is something of a scientific art, as you will see on these lovely animations. Now, there's, as you might imagine, lots of different ways of building these event sets. You'll be hearing of two different approaches later, with focuses on statistical and physical techniques, both having their merit. And I won't steal either of the other presenters' thunder here, but it's fair to say many models Verisk produces today are state-of-the-art hybrid solutions between statistical and physical techniques, with artificial intelligence, of course, as well, becoming an increasingly exciting tool in the box. Now, we build stochastic catalogs made up of at least 10,000 years and often actually much more. In this animation, we see an example of one stochastic hurricane track. Do it through again here. One stochastic hurricane track. And this stochastic hurricane track has its wind footprint upon its landfall over the United States, shown in parts of the Carolinas here. And you can see that we actually track these hurricanes throughout their life cycle to give a complete view of the wind footprint and potential damage and losses over land. And then the ambition here with these event sets, remember, is to fill in all the gaps of what's possible. So let's repeat this many times. Here's 3 more tracks and footprints showing storms with slightly different tracks, some recurving slightly earlier, some moving into the Gulf and making impact into Texas and Mexico. And we don't stop there. We repeat this, as I say, across 10,000 years at least, made up of a multitude of events that tell us about what's possible for the near-present climate. That is to say, what might happen next year. But note importantly that they remain physically realistic and rooted within the large-scale climate and weather dynamics. And we see that here. If you know your hurricanes well, you know that you typically expect them to move from east to west in the tropics associated with easterly trade winds, before typically recurving. In the 2025 hurricane season this year, we saw most of them recurve much earlier, and there was no landfalls over the United States, whereas in another year, you might see a lot of activity in the Gulf. So hopefully this helps you visualize the power of stochastic event sets. It's filling in the gaps of what's possible beyond what we've observed in history. And it's also telling us something about the frequency of different kinds of events in terms of their location, intensity, and other characteristics. Okay, so now we have different stochastic event sets for different models. And whilst we won't have time to go into them all today, let's look at a slightly different example, New Zealand earthquake. And the reason why I show this is because it helps put all the catastrophe model components together. So let's first look at this flowchart on the bottom of the slide here. Firstly, on the left, we generate events and define their intensity footprint stochastically before the engineering module determines possible damage from these events. Finally, the financial module then calculates a monetary loss. This is the final output of catastrophe models based on this damage and some policy conditions. And we can see an example in these animations where each frame is a different year of potential New Zealand earthquake events. So on the left, we've got the events themselves, and they have a certain size based on their magnitude. And then we have a certain intensity associated with each of these events, and that's computed based on the size of the earthquake and the soil type, for example, and more. Next, we can input some nationwide exposure data, which has a certain vulnerability to the hazard as determined by our expert engineering teams. And this is then all run through our financial module to generate an annual insured loss that we can see building in this distribution. As we repeat this over many years, we start to obtain a distribution of possible losses. And this is incredibly useful, as we are about to see. And we don't have much time, I'm afraid, to go into detail on the engineering and financial module components today. But these are crucial components to actually give you a final loss. And there's lots of good information and blogs online if you'd like to know more. So these stochastic event sets that I've just shown are incredibly useful and somewhat beautiful as well, I hope you agree. But how do we actually analyze all the information from them? What do they give us, so to speak? Well, analyzing thousands or millions of events individually, as you might imagine, is quite a lot of work. So the first point of call for most CAT modelers is to delve into the patterns they tell using something called an exceedance probability curve, or EP curve for short. Now, this represents the possibility of a certain financial loss being met or exceeded in a given year. We can visualize this on the right-hand side of this slide with this graph. EP curves are usually constructed with decreasing probability or increasing return period as you move right along the y-axis, x-axis rather, and increasing losses as you move up the y-axis. Note a return period is simply the reciprocal of the exceedance probability. Now, EP curves for different perils can often take on different shapes, as we see here, depending on their hazard characteristics, such as frequency. One peril, in light blue here, may be expected to produce losses of $1 million or more every 5 years to a client's portfolio, whereas on the dark blue here, we can see that maybe a different peril only produces losses of $1 million every 25 years on the same portfolio. And maybe where you're sitting right now, you can think about different natural perils, hurricanes, earthquakes, floods, thunderstorms, and so on, and think what kind of shape they might have. Is the risk dominated more by frequent events at the low end of the CP curve, or are they more dominated by extreme events as we get up towards the tail of the EP curve? Now, each of the points on this EP curve represents the loss from an individual year in our stochastic event catalogs. The average annual loss is one of the most important metrics one can derive from these EP curves. This is the loss that can be expected each year on average from a certain peril. And this is equal to the area under the EP curve. And metrics such as these are important for insurers across the spectrum of use cases, which we will discuss a little bit later on. Now, let's show an example of how we at Verisk actually can generate stochastic event sets. We'll start by considering the history of cat models up to the present day before delving a little bit into what's coming up in the future. So at Verisk, we invented catastrophe modeling back in the 1980s and initially built models for the United States, such as hurricane cat models. But as big events have occurred over the years, and we can see some of the big hitters on this slide with the years that they occurred in, and you will have heard of many of these events, of course. Over this time, Verisk has continued to build on and improve its suite of catastrophe models, from extratropical cyclones in Europe to earthquakes in New Zealand and Japan, floods and severe thunderstorms, where we have seen record-breaking losses in recent years, with $60 billion in the United States in 2023. Now, as big events have come along since the dawn of cat modeling, this has reduced the risk of insolvency substantially, as we see here. And this means basically insurers are now much more prepared for a range of catastrophe scenarios. So this just shows the power of these stochastic event sets and catastrophe models within the insurance industry. Now, what about the future? You might be interested in what we're building today and what we're continuing to build. And the next generation of atmospheric peril models will stem from a combination of artificial intelligence, large physics-based simulations, allowing for thousands or hundreds of thousands of years of stochastic events. And this all starts with a global model which has real physics and teleconnections between perils. But it has some disadvantages. It has, slightly coarse resolution, and we know there's biases there. So this is where we can bring in our reanalysis data, again, our best estimate of the historical atmospheric conditions, gridded over the entire world. And what we do is we bring this GCM to be more reanalysis-like by using AI, machine learning techniques. And this is actually machine learning-based neural networks, to be precise. And we use these to debias and downscale the original GCM for example, a regional simulation like a Europe domain. And this is what we call our global model and has been in development for many years now at Verisk. After some further expert modeling, this will actually allow insurers and the users of these models to have a better understanding of the impact of compound risk events to their portfolios. So we can see here that we have events from ETCs, extratropical cyclones and severe thunderstorms from floods. And these can often co-occur. And what this global model allows us to do is allows us to consider the impact if they're to occur at a similar time, because it's all coming from the same underlying physics, the same underlying weather patterns. Okay, so now we know why cat models are useful. We know what they are, and we know a bit about how we build them and are looking to build them into the future. So let's end this presentation by discussing some real-world examples of how cat models are used. So, as you're about to see, catastrophe models are used across the insurance chain. And there may be slightly more to this than you originally thought, right? So for sure, cat models can be used for pricing risks and insurance policies, but also managing portfolios in a much broader sense. Remember, an individual insurer may have a very complex book of business. And at the end of the day, they also want to make some money. So cat models can help them anticipate where to build business and look for opportunities, and indeed which risks to actually select. Cat models also help with knowing how much capital or money in the bank an insurer needs to be able to pay out in a worst case scenario. Now, this is usually set around the 200-year return period. So if you think back to that exceedance probability curve I showed you a few slides back, that 200-year return period is often one area on that EP curve that insurers will look at first in order to understand how much capital they might need for that peril region. Furthermore, cat models are vital for supporting insurers with regulatory reporting requirements. And these actually include intensive exercises to make sure insurers are prepared for any scenario and thoroughly understand their view of risk. So all of this is helping reduce the risk of insolvency for these insurance companies. So with that, we see that the stochastic event sets that underpin catastrophe models are crucial components of the insurance industry. We've summarized today the what, the why, and the how, showing that insurers have an onus to understand the risk that they underwrite. They should have sufficient funds to pay out any valid claim in the event of a catastrophe or sequence of catastrophes. And we've shown how stochastic event sets are incredibly useful tools to do this. They fill in the gaps of what's possible in today's climate. Going forward, we'll likely see much more artificial intelligence in cat modeling, machine learning techniques. We've shown an example of how combining machine learning with large global model, a GCM, allows for a fast-running, dynamic, and correlated model. So with that, I'd like to thank you all very much for your attention. Please pop any questions you have in the chat if you haven't already, and I'll do my best to answer any a little later on. And there's some details on this slide here in case you want to know more, or feel free to get in touch as well. And I'll stop there. Thank you very much.
Thank you, Alex. That was a really great overview. Just repeating what Alex said, reminder to put questions in the Q&A tab. So next, we've got Callum Murphy-Valtrop, who completed his PhD at Lancaster University in statistics and the Statistics and Operational Research Department. That's a mouthful. And is now completing a postdoc at TU Dresden. Callum, if you want to take it away. Alex, you need to stop sharing your screen. I think. There we go.
Cool, let me try that. Okay, can you see my screen?
Yeah, perfect.
Perfect. So yeah, thank you for the introduction and the invitation to be here. It's a real honor. So yeah, my name is Callum and I'm based at TU Dresden and SCAD's AI. And I'm going to talk kind of very closely related to what Alex spoke about how we generate these extreme event sets, really focusing on that extreme part here. In particular, focusing on the statistical background, because that's my background in my research. So as mentioned, I did my PhD in statistics at Lancaster, finished in 2023. Before that, my background was in mathematics, so I was kind of trained in pure maths and then moved into more applied stuff as it went on. I have some experience also, so I worked at Fathom, who are a flood risk intelligence company based in Bristol. I did a placement there in 2022, so I have a very small amount of experience in industry, but my background is more academia and modeling and statistics. And since 2023, I've been a postdoc at TU Dresden and SCAD's AI in Germany. SCAD's is a new center in Germany. It's the Center for Scalable Data Analytics and Artificial Intelligence. It's one of 5 new AI centers funded by the government. So they're really trying to stay ahead, really trying to make sure they're prepared with AI machine learning for the future and what may come. And hence they're kind of throwing money at anyone doing AI research. So because of that, my current research focus is really on employing these kind of techniques, machine learning, AI, in the context of modeling extreme events, extreme value theory, my background. Furthermore, not just like in my kind of research background, but also my personal background, I suppose, I'm really passionate about working both with industry practitioners and also applied researchers. So I still think there's a lot of barriers, unfortunately, that do hinder communication. I do find people on my side, the more kind of theoretical mathematicians, can be a bit elitist and a bit kind of like unwilling to communicate quite complex ideas because they think, oh, we're so clever, we can understand it. And I really despise that. So I really try and kind of make sure whatever I do is open source, and I try and make sure that I can communicate this stuff with people who are also applied and also working in industry, working for governments and so on. So I think there's a real kind of like need to get people working together. And I really think there's this interconnection here that if you want to do any of these, you need to have some understanding of every link in the chain, if that makes sense. And I don't see the point in doing kind of this side of things. Oh, sorry, I don't see the point in doing theory unless there's some kind of like useful practical tool you can apply it to in the end, right? So for me, it's all kind of all one. So quick overview, I'm going to talk about extreme value theory in general. It's both univariate and multivariate extremes. Then go on to discuss two different competing modeling approaches. One is called the conditional extremes approach. The other one is called geometric extremes, a very new approach. Then I have a quick discussion and kind of outlook on future ideas and consideration. So why? The question has already been really well answered by Alex, so I won't spend too much time on this, but we have very limited data typically. And we need these kind of event sets for modeling, analyzing systems under uncertainty. And particular interest are extreme events, right? Because by definition, if you look in historical data, there'll be very little data that is extreme, that's really big or really small. So we need to make sure we can kind of understand these events in particular, and we can account for these in the stochastic event set generation. My particular problem then is to say we've got two variables or more, in this case, X and Y, but you could have however many you want. We've got some sample, so xi, yi from I1 to n. I'm going to say n is quite limited, as we don't have much historical data, we don't have much data to work with. We want to kind of fit some model across this data to try and generate some more extreme events from X and Y. And it's a question of how do we do that? Well, for that, we need extreme value theory. So why do we use extreme value theory? Well, it provides a nice theoretically justified modeling framework for capturing these kind of events, which we see not too often. So I'm talking here like floods, heat waves, and droughts. And this is very important. So for example, I've got a picture here from Dresden. The left side is on a nice, I think, spring or summer's day. I took this picture myself. So this was kind of, nice conditions. You've got the Elbe, the river here, where things were kind of behaving as they normally would, pretty standard day. And we had some flooding last year. So you can see the kind of the big change that goes from having a normal day, quote unquote normal day, on the Elbe to a day with heavy rainfall and then flooding from, there was a lot of rainfall in Czechia as well, and that kind of flowed down into Dresden. You can see it's a very kind of big impact on the city, so making sure we can understand events like this one is clearly very important. And crucially for this context, right, if you've got a model for the extreme data, it gives you some means of stochastically simulating extreme events and therefore extrapolating into that tail. So univariate extremes, when I say univariate, I mean just one variable, right? This is very well established. So you pick kind of one location or one particular process like temperature, and you can do what's known as a peaks of a threshold approach. In this case, we just fit a generalized Pareto to the observations of some high threshold. In equations, I've only got 3 equations in my slides, so don't get worried that it's going to be lots of maths or whatever. But the idea is you have a threshold u, you condition on the variable x being bigger than that threshold, and you say the exceedances of that follow a generalized Pareto, which has this form here. Easy in a picture, so we've got some data, we've got x observed over time. We pick a threshold, and we say everything above that threshold, so the red line here, is extreme, and we'd fit a generalized Pareto to the green points there. And there's some very good, like I say, theoretically justified reasons for doing that. But in many contexts, and I would actually probably say most contexts, we don't just care about one variable or one location. Extremes can occur across different variables at the same time or different locations at the same time. So we want to understand the different relationships that can occur between the extreme events at different locations or between different variables. So when we talk about multivariate extremes or multivariate extreme value theory formally, what we really refer to is the study of dependence between extreme events. So I've got like a Some example here, you've got the Elbe, which runs through Czechia, passing through Dresden, eventually reaching Hamburg, and then the coast, the North Sea. One could pose the question, what's the probability we get a flood in Dresden, or what's the probability it floods in Hamburg, given we had a flood in Dresden? Because they're on the same river, they're going to be interconnected, there's going to be some dependence there, but it's not going to be like perfect correlation. There's obviously going to be some variability depending on local conditions and so on. So we want to be able to understand kind of the joint relationship between different extremes. There's also a question here, which is a bit tricky to answer because there's no one size fits all answer. Like, what do we mean when we say a multivariate extreme event? So in a very simplistic way, if you have two variables, x and y, you could just look in the top right here and say, well, when they're both big, that's when we pay attention. But also you're kind of missing out some particularly important regions, like the region here, the blue region, where x is big, but y is not so big, and vice versa, when y is extreme and x is not so large. And in many cases, actually, these events, like maybe this point here, can be really important. They can be very high impact still. So just focusing on this kind of this orange region is quite limited. How we define what we mean by a joint extreme, there's no easy answer. There's no ordering here. You can't say that this point is bigger than this point because you've got two variables rather than just one variable. There's different definitions out there, right? So that it's, like I always say, it's kind of a philosophical question rather than a kind of a mathematical question. But the classical approaches within multivariate extreme value theory tend to focus on that orange region. So they really tend to focus on kind of modeling data here. If that's your interest, if that's kind of where your application is, that's fine. But in many contexts, we don't just care about these events. We also care about events here, perhaps here. And also we may want to look down here and say, well, what about the lower tail? What about the kind of events in between? So I would say kind of focusing on that orange region is quite limited. And furthermore, these kind of classical approaches, it's only been around since about the 1980s or 1990s, this kind of research, this modeling. They're just applicable when you've got the extremes, different variables or locations occurring simultaneously. That means they always occur at the same time. And there's some cases where that is a reliable assumption, but there's many cases where that's not an assumption which we can make. Say I'm thinking temperature and humidity, it's not always going to be a peak of temperature when you've got a peak of humidity. There'll be some cases when that's true and other cases when that's not true. So that's just not realistic, this assumption for environmental data, and hence many recent methods have tried to overcome these two limitations for applied modeling. So in this talk, like I mentioned, I'm going to discuss two contemporary modeling approaches, the conditional extremes framework and the geometric extremes framework. And both of these can be used for stochastic event set generation to generate as much data as you would like to look at the joint tail. Okay, so first up, we have the conditional extremes model, which was first proposed back in 2004. It's actually a very simple idea. It's basically you condition on one variable, you pick one variable out of a number of variables or however many you have. You say, okay, we'll look at that variable, we condition on that variable being big, and then we perform regression on the remaining variables. So it's a very simple kind of regression model, very similar to linear regression. And there are some good, it's not just kind of a simplistic model, there's some very good theoretical reasons why they make those assumptions and why they kind of decide the model should look that way. And this is a very popular approach for event set generation and cat modeling. Bunch of references there. Don't worry about noting these down. If you want to kind of get the references, I'll put the slides on my website and you can get them from there. So to put the model in an equation number 2, promise. We have the framework here. So we've got two variables, x and y, and we're making the following assumption. So we're going to fix x to be a high value. So we're going to say the small x here is quite large. It's an extreme event for x. We condition y on x being big, then we assume the following form. So we assume that y, given that x is big, follows alpha times x plus x power beta z. I'll explain these terms. So x is the conditioning variable here. Z is some residual variable. We don't observe that. That's kind of a residual process. Alpha is basically the slope of the regression line. So is it going up like this? Is it going along like this? Is it flat? Is it kind of steep? And beta is simply the spread around that line, like how, is it following the line parallel? Is it kind of converging or diverging? Basically what we do is to fit this model, we assume a distribution on Z. So we assume that follows typically a normal distribution. We then use likelihood inference to obtain estimates of alpha and beta, these kind of slope and spread parameters here. And that then allows us to extrapolate into the joint tail. It's really easy to see in the picture then. So we have two variables, let's say x and y. We condition on x being above some high threshold. So the green line here, we're saying that's the threshold, and we look at all the x values such that kind of it's larger than the green line. So all those red points there. We then fit some regression lines. We estimate alpha and beta. And that gives us lines like these ones here. So we then have kind of lines we can regress on and which we can simulate new data on. The process for simulating then is very simple. You generate an x value from the tail of x, so some value within this region here. You sample z from the observed residuals. So you have your kind of computed residual process, and you kind of just generate or sample randomly from that. And you set y, the kind of the other variable, the non-conditioning variable, equal to alpha x plus x to the beta times z. And that gives you a picture like this. So the red points are the original data. The blue cyan points are the ones I've simulated using the model. And you can see they match up pretty well with the observed data process. So it kind of gives you a means of extrapolating into that joint tail from quite a simple idea and modeling framework. So this easy extends. I've done everything in the kind of the two variable setting, the bivariate setting, because it's easier to illustrate. But everything will extend to the higher dimensional setting. So you can kind of do this in the same way. All you do is kind of fix the conditioning site, and you can condition, you estimate alpha and beta for all possible pairs with that conditioning site. Then you can get extrapolation into the whole joint tail rather than just looking at two variables. But the only thing to mention here is it's only applicable. You have this kind of condition that one variable has to be big, it has to be extreme. Let's go back to this picture where I have a conditioning on y being extreme. We could like kind of look at this region above this line here, or we condition on x being extreme, so we condition on everything being above this line here. Now that's again fine if that's kind of relevant to your application, but there may be some cases that's not super relevant. And also, what do you do for this region? Do you condition on x? Do you condition on y? It's kind of ambiguous which variable you condition on, and there's no kind of good guidance for picking the conditioning variable. So now I'm going to talk about geometric extremes, which I like to think kind of provides a natural avenue for that question of, you know, how do we pick a conditioning variable? Or in this case, you don't actually need to pick a conditioning variable. So it's a very new modeling framework. It's only really been around since 2022, I would say. And it's a very flexible framework for modeling joint extremes. The basic idea is, rather than doing what we did before, just sort of saying we care about the top right region, or we condition on one of the variables being big, we just say we care about every region where there's a low probability of observing data. So for this data here, x and y, you've got the gray points, and we're looking kind of near the boundary of that data. We're saying all those kind of points which are, you know, unlikely to be observed are relevant for our model. So not just looking at the top right, but also at the bottom left, the kind of the lower tail as well as the upper tail, then everything in between. So it's a kind of a different definition. Like I say, it's a philosophical idea, how you define these events, but it's kind of a more general definition, let's say, of a multivariate extreme. The geometric word here means we're going to split the data into angular and radial components. That's the key idea behind these approaches. And I've showed in pictures as well. So what you do is you do this decomposition, you decompose into angular and radial components, then you model the radial component conditional on a fixed angle. Okay, that's the basic idea. Again, I'll show everything in the picture. There's many different competing approaches for how we do this modeling. It's not kind of quite clear cut. So we're going to restrict attention in this talk to one approach, the so-called SPAR approach, but note that there are different ideas here, and there's kind of, yeah, because it's so new, there's still not best practices really established. So how do we define angular and radial components? That is basically a question of how do we define distance. We're going to use the Euclidean norm because it's very standard, but there's different approaches for doing this. So we have our variables x and y, and we're going to define radial and angular components as follows. So for the radial component, we just take the Euclidean distance. We take x squared plus y squared, the square root. So if you remember Pythagoras' theorem from your maths course in the past, that's the hypotenuse of the line, the vector xy. Theta then is just the arctangent. So it's looking at the, if you take the vector of xy, look at the angle from that line to the origin, or not the origin, the axis. So in a picture, we have x and y as some data. If we look at this point here, the angular radial decomposition is really simple. The radial component is simply the length of that line from the origin. So the length of that blue line, if you just measure that with a ruler, that gives you the radial component. And then theta is the angle between that line and the axis here. So very simple when you see it in a picture. So you can take your data, this is on the kind of original scale of x and y, and you decompose it. So you transform it into radial and angular components. We've got the angular component on the x here, and the radial component on the y. And basically the idea is as you change the angle, it changes the kind of the part of the two-dimensional space which you're looking in. So are you looking in this direction? Are you looking in this direction? Are you looking in this direction? So on and so forth. So the angle gives you the kind of the direction of the data, and the radial component is how far out from the origin is each data point. And joint extremes can be characterized by that behavior. So if we're looking at r and theta, so the radial and angular components, you can kind of say that the theta, the angle is given the direction, that joint extreme, whereas the radial component is given the magnitude, like how big is that joint extreme event. The SPA model then, final equation, this is the semi-parametric angular radial model. So the basic idea is very simple. We fix an angle and we say for the large values of the radial component, these follow a generalized Pareto. So what I said at the start with univariate extremes, it's the same idea, but just in the kind of the multivariate setting. So in a picture, we fix an angle. So say we fix pi/4 just here. And we say the large radial values, so the radial values when you get really big, so that's kind of the top part of this line, follow a generalized Pareto. This is a very similar idea to what we saw right at the beginning. We then have different kind of means of obtaining these various modeling parameters. So we have to estimate kind of parameters for the model as well as a threshold. The threshold is estimated using quantile regression techniques. I'm going to leave out the details for the moment, but I would kind of refer to these references if you're interested. Then the parameters are estimated using something called the EVGAM framework, which is basically like a likelihood inference framework. So let's see in a picture. So we have our data. So we're on the radial angular scale, so angle, the radial component. We have a threshold, which is now varying over the angles. It's not a fixed threshold, rather kind of an angular dependent threshold. So you can see the red line here is our threshold. We say everything above that threshold follows a generalized Pareto. That's the basic idea of the model. You can then put it back on the original scale of X and Y, and then you kind of fit the model to these green points here, which then allows you to extrapolate into the tail. Event set generation then is really simple. You simply draw an angle to begin. So you draw a theta from the observed angular process. You draw a radial value from the fitted generalized Pareto, so that model I mentioned. And then you set X and Y equal to r cos theta, r sin theta. That's simply the relationship between the radial angular components and the original data. And you get something like this, right? So you end up with data simulated in the whole joint tail, not just kind of looking up here, but kind of every region, every angle we could look at. We can simulate and generate new event sets or new observations. It's kind of a very flexible way of generating this stuff. So methodology, like I said, it's very new. It's currently, actually to change this slide, I think yesterday, because it was only available up to d = 10, and there's been new papers out this week, so it's now kind of, there's now methodology out which kind of goes up to 20-dimensional data. So it's improving very rapidly and changing very rapidly. It's a very exciting hot topic within the context. It gives you kind of a way of capturing the whole joint tail rather than just a particular region. So I think it's kind of a nice approach for this kind of modeling. Which approach should I use then if you were kind of picking between these different ideas? Well, that's kind of, again, a question of what do you want to look at? What's your focus? Do you care about a particular region of the joint tail? Do you care about all kind of joint events that could happen? Or do you care about both the upper and lower tail? There's different kind of questions to ask it before you fit a model. Of course, there's no one size fits all. That's always a caveat to anything like this. You can't just say this is the best model and everything else is trash, right? It's worth noting that geometric methods are still very new, and I don't think there are best practices, as I mentioned before, but I think they will be established in the next 2, 3, 5 years or so. But the one thing to mention is I do think conditional extremes are likely to be supplanted in the years to come, given we've got these kind of more flexible, fancy approaches for doing this modeling. Finally, just a picture to kind of do the comparison between the two of them. So we have on the left the kind of conditional model, and the right is the geometric or SPA approach. First of all, we fit a threshold. So in this case, we're fitting just a line here. We're saying everything above that line is our interest. On the right side, we're kind of estimating this set, this kind of blue set, and we're looking outside of that set, so the gray points outside of there. And from both of them, we can simulate, we can get kind of data which is in the joint tail in some way. But what I would say is actually when you can look at it like this, you realize you get the kind of first approach, the conditional idea, directly from this geometric approach. If you're just going to simulate data, then you say, I want to focus on X being larger than 4, you can do that. You can just kind of focus on that region. It gives you the kind of conditional approach for free to some degree. That's why I do think this approach, whilst it's been very useful, will be supplanted in years to come. That's why kind of, the geometric stuff is kind of very nice and very general, I think. Final kind of considerations then before you go about fitting these models, there's a bunch of stuff you have to consider, which I've kind of glossed over. So first of all, a lot of these models tend to require a marginal transformation. So moving everything to a standard scale and then fitting your model. And that's non-trivial and can be quite tricky, but it's very important. You need to make sure you kind of capture the marginal behavior before you transform to a unified scale for fitting the model. Selecting the threshold, that's a really big point. So what I mean by that is how high do you put this line? So at this point, I think it's x equals 2. But you could obviously put it x equals 5 or x equals 10. The issue is the kind of the further or the more extreme you make that threshold, the less data you have. And then if you don't have much data, you can't really fit the model with any degree of accuracy. There's too much uncertainty. If you put the threshold too low, then you have more bias. It's a kind of a bias variance trade-off. You always need to consider how high or low do you put that line, do you put that quantity. Sample size, general one, but you need enough data. And what I mean by a reasonable amount of data, that there's no fixed definition. But when you work with extreme value models, you already have less data because you're kind of conditioning on things being extreme. So you need a reasonable amount of observational data or kind of model data to work with before you go about fitting model. 2 questions then, are your data independent? A lot of these models assume that data are independent. That's very rarely the case in practice, but there's various methods out there for accounting for dependence in data, like temporal dependence. Just make sure you check that before fitting the model. And also, are your data stationary? Are there trends in the data? There may be seasonality, there may be long-term trends. Again, a lot of the models only tend to work when you've got kind of stationary data. You need to make sure you either detrend the data or you only fit to a kind of a certain season or so on. And again, there are kind of other methods as well for accounting for trends directly within these models. Some references, I'm not going to stay on this slide for long. All I want to say is if you want to look at these references, these slides will be on my website, so please feel free to go and check them out. So yep, please, if you want to learn more, the link is just here. You can also Google my name. I've also, for anyone who wants to just play around, the picture I showed comparing the 2 approaches, right, that's on my GitHub. So you can go and like get the code, see how everything actually works under the tank, see how you would fit it kind of it's on R as well. So if you want to kind of play around, I think the best way to learn is always by playing. So just go around, check out the code and see if it works for you and try to understand if you would like to get a better sense of what these models are really doing. And final, word of caution. Okay, so we always like to say this kind of quote from George Box that all models are wrong, but some are useful. So whatever you do, whatever model you use, whatever fancy technique, always make sure you rigorously validate and check that model with diagnostics and metrics, right? Don't just kind of fit the model and say, well, it's a nice model and other people have done it, so it should be nice. You need to double check. Like in the context of this picture, right? Is the cat kind of easily walking in and kind of snuggling down and then being quite comfortable? Or is it being like rammed into the box and really struggling to be there? It's a question you always need to consider when you're doing this stuff. So yeah, thank you very much for listening. I'm sorry if I've gone over with time slightly, but yeah, happy to take any questions at the end.
Perfect. Thank you, Callum. That was really great. I've never really understood having a tall model. Now I do. So that's good. Great. As Callum said, questions in the Q&A box. We've got some good ones for Alex, so if we could keep them coming, that would be great. Final speaker, we've got Julia Lockwood talking about physical event sets. Julia got her PhD at UCL in the physics and astronomy department and is now a senior scientist at the Met Office. Julia, take it away.
Hi everyone. Right, I'll just attempt to share my slides. Here we go. Can you all see this? Sorry, I can't see anyone. Can you see this?
Yeah, all good.
Yeah, okay, yeah, sorry about that. Right, thanks very much. And yeah, thanks for inviting me to speak today. So yeah, as Colin said, I'm going to talk about physical event sets, and I'm mainly going to talk about this via an event set we made a few years ago for European windstorms, but hopefully some of the lessons that we learned and the advantages and disadvantages of making event sets in this type of way can be applicable to other hazards. So for the event set that we made, we used the output from a set of global climate models. And I'm sure many of you are familiar with these types of models, but I'll give a quick overview of the physics involved. And it's basically for a given set of initial conditions and boundary conditions, you solve for the evolution of, in the atmosphere, it would be for wind, temperature, pressure, and humidity. Those are called the prognostic variables, the ones that appear in your differential equations. Then from those variables, you can derive, everything else you want to know about the atmosphere, like precipitation rates, snow cover, cloud cover. They're all derived from your prognostic variables. And for the atmospheric component of a climate model, most models will have a formulation of the governing equations, which look something like this, which I'm not going to go through all the detail, but they're basically derived from the fundamental physical principles of conservation of momentum, conservation of mass, conservation of energy, an equation of state, and conservation of moisture. And what you also need to take into account is the climate system is not just the atmosphere. You've got different components like the ocean, vegetation, atmospheric composition. These all have to be taken into account as well. For example, the ocean is going to have momentum, heat, and moisture exchange with the atmosphere. So that's going to appear as sink and source terms in these equations here. And you can run these climate models at varying levels of complexity. For example, you could have everything interactive and fully coupled, or you could run it with, say, fixed sea surface temperatures and just model the atmospheric component. But as you can see from these equations, they are incredibly complicated and they are highly nonlinear. So that means the atmosphere is a chaotic system. So if you run it with a different set of initial conditions, then you can get a completely different outcome. So in our climate model, you can run it several times, just varying the initial conditions, and you can get a completely different set of, of windstorms or hurricanes. Also, even if you just, formulate the equations in a different way or have different ways to parameterize the subgrid processes, all of which could be equally valid, but that will give you a different set of results. So this is very good for, a byproduct of this is you can generate a stochastic event set just by running a climate model, either for a very long period of time or just repeated versions of the same time. So for the event set that we made, we used the models that were run for the Primavera project. And this was a project that finished a few years ago now. And it was about developing and running high resolution global climate models. So these models was higher resolution than the typical CMIP6 models, which were used for the last IPCC report. And there were several different modelling centres involved. Excuse me. So we had 7 modelling centres in total. We used the output from just 5 of those models, as they were the only ones that had the variables that we needed. And each modelling centre run at least 2 different versions of their model, one at a low resolution, which might have a grid spacing in the atmosphere of about 100 kilometres, and a higher resolution version which had grid spacings of around about 25 kilometres. And some of the modelling centres ran, the Met Office one ran 3 different resolutions, and also some of the models ran multiple ensemble members. And we used the simulations that were the historical experiments. So they ran from 1950 to 2014, and they ran from 1950 to 2014. So totaling that up, we've got 64 years of data for each of our runs. And if you add up all these ensemble members, that's 21 different versions of 1950 to 2014, which gives us about 1,300 years in total. So it's not quite the 10,000 or 100,000 years, but it's still a lot more than the observations that are available. So to make our event set, we're looking at European windstorms for winter. So we tracked all the extratropical cyclones in all that, 1,300 years of data. And then we made a storm footprint we identified all the tracks which entered Europe during the extended winter period. So that's October to March. And these storm footprints, the standard definition is it's a map of the 3-second maximum gust over a 72-hour period associated with each storm. And the idea is that people from the insurance industry or risk modelers could take this set of footprints that we've generated and then use that as an input to one of their catastrophe models and estimate expected losses from windstorms. But one of the issues we encountered was that the 3-second gusts weren't available for all of the models. They just would have the daily maximum wind speed. So we had to make the footprints based on the wind speed and then convert to gusts afterwards. So in addition to having to do this conversion from our surface winds to the gusts, we also had the issue that all the models are run on different grids, and some of these are, quite low resolution grids. I think insurers would typically want, quite a high spatial resolution, and also some of the models show a bias in their surface winds, especially at high altitudes. So we needed to correct for all of these factors. And we did it all in one step, which was to use a quantile mapping method. And this was essentially, we took ERA 5 reanalysis data as our observations, which I've put in inverted commas here because I know, as Alex mentioned earlier, reanalysis can have some issues. There can be some differences between reanalysis data and data measured at weather stations, but we're kind of we have to use a gridded data set with a continuous time series, so we didn't really have much choice of that. And essentially what we did to convert our winds to gusts was for every grid point in our ERA 5 reanalysis dataset domain over Europe, which has a grid spacing of about 17 or 18 kilometres at these latitudes, you compare the distribution of the daily maximum gusts in the reanalysis with the distribution of the daily maximum winds in each of the models. And this is done at each grid point separately. And we essentially just fitted a function to map between those two variables. And this is an example of the raw wind footprint from for one of the storms from one of the models. And this is after we've done our conversion to the gusts. So you can see there's a big increase in speed as you go from winds to gusts, which is to be expected. And you're also adding in a lot of the finer scale detail. And these are some of the footprints that were generated from the model. So on the left, we've got footprints from the reanalysis data. So this is just some examples of real events that occurred. So we've got the famous windstorm Daria in 1990, Anatol in 1999, Klaus in 2009, and 87J, or the Great Storm of 1987. And we just had a check to see, because these observed storms had quite different characteristics, and that Daria covered a very large area over Europe. Anatole was more of a narrow but very intense storm. Klaus was unusual in that it hit further south, the Iberian Peninsula in southern France. And 87J had this southwest northeast track rather than just a west to east one. And we checked in our event set whether the model was capable of simulating all these different types of storms. So here are some of the matches we found to each type of storm. So you can see it gets the Daria-like storms, the Anatole, narrow ones hitting Iberia, and then the ones with the track coming from the southwest. And in total, we had nearly 270,000 footprints from all of this data. But this huge number is because the tracking algorithm that we used it can pick up very weak events. So for each of our footprints, we calculated a loss index for the windstorms. We used the Claver and Ulbrich one, which is essentially your maximum gust above the 98th, a local 98th percentile threshold, the cube of that multiplied by your population and density and area, and then you sum that over all grid points in the domain that you're interested in. So that's this red area here. And when you calculate that, we found if a footprint doesn't have a gust which exceeds the 98th percentile anywhere, then it has a zero loss index. So we had about 70,000 footprints which have a non-zero loss index, and about 2,700 of these would be classed as severe. And comparing that to our Era 5 data set, which covered only 35 years, then we've only got 69 severe events. So we've increased the number to calculate statistics on quite significantly. So for some of the verification that we did on the data set, here we've got the return period curves. This is a bit like the exceedance probability curve that Alex mentioned in the first talk, except we've got a return period on the bottom here. And this is the aggregate loss per season. So we've just summed up the loss indices from all of our storms in a given season. And the red dots here is the data from our stochastic event set. So each dot represents a season. And the black dots are the data from the Era 5 data set. So we've got 35 dots there. And on the right, this is just zooming into this the left-hand side of this plot, which is where we've got the Era 5 data. And you can see that the black dots, the Era 5 data, does lie outside of the Primavera, the fit, which is this red band here to the Primavera data. But this is simply an effect of the sampling uncertainty of having 35 years. So to test this, what we did was to take from our 1,300 years of Primavera data, we'd sample 35 years of that data and then calculate the return periods of those seasons, and then do that, thousands of times. And this is the 95% range of return periods that you get when you've got only 35 years of data. So our black dots lie within that range, which shows that our Era 5 data is consistent with the Primavera return periods. And some of the benefits from a dynamical model is, as well as generating, these nearly 3,000 severe footprints, you also get the date that the storms have occurred. So you've got information about, how many storms did you have in that season? How close together were they? Also, what else is happening elsewhere in the globe? So here we were just testing whether the models can capture storm clustering, which European windstorms are known to be clustered in that they don't follow a Poisson distribution. You can get some seasons where you have a much higher number of storms than you'd expect from a Poisson distribution. So here we've got in black, that's our era 5 number of severe storms per season. You see this one where there were 8 storms in a season. I think that was the 1990, which is a very severe one. And then this is the distribution we get from the Primavera data set in red. And these vertical bars, again, they show the sampling uncertainty that you would get if you just sampled 35 years of Primavera data and then calculated your bar chart with that. And you can see that the black lies within the 35-year uncertainty, again, showing that the model is consistent with the observations. And another benefit, as well as knowing the timing of the events, is you can associate your events with things like large-scale climate indices. So here we looked at aggregate losses and number of windstorms for different NAO phases. So the North Atlantic Oscillation. So the NAO, or North Atlantic Oscillation, is basically the pressure gradient between Iceland and the Azores. So it's this pattern here. And when that's positive, you generally get a northward storm track going further into Northern Europe. And if it's negative, your storms tend to go into Southern Europe. And the reason for looking at this is that the NAO has some predictability on seasonal to decadal timescales. So you could, for example, if you know there's a prediction of a positive NAO this winter, you could condition your event set to look at what, how might that affect the losses that you expect for a given winter. So these are the aggregate losses per season against the NAO. Again, we've got era 5 in black and our model data in red. And this is for the UK. And you can see when the NAO is positive that you get a higher probability of severe seasons. And the same for the storm numbers per season. When you've got the positive NAO, you've got a higher probability of having a higher number of events. And we looked at this for several countries across Europe. So we've got the Northern European ones here, and they tend to show positive NAO, higher losses, whereas for Spain and Portugal, it's the other way around because your storm track is deflected southwards. And again, these bars show that the observations are consistent with our Primavera data set. But some of the issues we encountered, however, are that the results, there is a sensitivity to the bias correction, or well, the way we converted from our winds to gusts. And so I mentioned that we basically fit a function. It was a GPD, a generalized Pareto distribution, as Callum mentioned in his talk, to convert between the winds to gusts. We tried another method where we just fitted them empirically. We mapped the quantiles empirically. The disadvantage with that method is that you can't get gusts any higher than have been seen in the observations. And this is a plot of the loss index from each storm using this empirical bias correction method compared to the original one that we used. And this is the one-to-one line in red. So there is a very strong correlation between the two, but the method we used does tend to have higher loss indices. And also there are some storms for which the losses go to, or the loss index goes to very extreme values. And I think these are probably untrustworthy, or there's definitely huge uncertainty on what the actual loss index would have been for these storms. So because of this, we think this event set is probably not, it's not advisable to use it to answer questions like what is the worst storm ever that can happen in this 1,300 years, because it's going to, it's this one, and this has absolutely huge uncertainty. Also, you can't really say what's the maximum gust you are going to get at a grid point, because essentially you'll get the same answer as you would if you did a generalized Pareto fit to the era 5 data, because that's what we fixed it to. But on the other hand, I think questions it could help answer might be how many times, what's the frequency of storms with a loss index of, say, Daria or greater. I think there'd be more confidence in the number of storms above thresholds rather than the actual magnitude of their intensity. And of course, one of the other major disadvantages is the computational expense, and that's not only in running the physical model, but also the data processing that's involved is extremely time consuming. It's, you know, terabytes and terabytes of data. So yeah, just to summarize, physical stochastic event sets, they can be very useful tools for understanding risk. I think their main advantage is they give a full picture of the evolution of an event and the current climate conditions. So that could be global climate indices like El Nino, or it could be other events across the globe. And I think the main disadvantage we encountered was this need to bias correct and downscale, which can create large uncertainty on the most extreme values. But I think since we developed this event set, you know, there's been this explosion in AI and machine learning. And I think if we were to do this again, we might do something like to take the large scale conditions from the climate model and then use a machine learning algorithm to downscale that to surface gusts. And below here's just a reference to the paper in case anyone wants more information. But yeah, that's the end. Thank you very much.
That was great. Thank you, Julia. Okay, perfect. We're going to move on to a Q&A now. So keep questions coming in on the Q&A tab. That would be great. And I'm going to take the privilege as host to go first. So I suppose there's sort of a huge variety of methods that we've spoken about. And ultimately, we want these methods to be suitable for decision making down the line. So I suppose the question is, how do you build confidence that those methods are going to be suitable for the decisions that you're making? And we'll start with Alex.
Sure. I think, you know, I obviously have the vendor perspective. So we build the models, and there's a lot of internal validation work that we will do in order to build confidence in our stochastic event sets and in the models we've built. There's a second component to this, which of course is how insurers and the people who actually look at the models, how they actually build confidence in the models. And that's almost a separate question. And a lot of the techniques we might do are similar, but there's sort of no easy answer to both of those. But a lot of ideas, just to rattle a few off. So we'll obviously always do our due diligence in terms of validation against any third-party data sources that we can access, looking at frequency over history, comparing to frequency in our stochastic event sets. Does it seem reasonable? Doing similar things for intensity distributions. And this is the kind of analysis that those who use our models will also be performing. And a lot of it is, very much at the state of the art of science, using the recent literature, new data sources as they come out, thinking about impacts of climate change and what if you include this additional year, etc. So all of that kind of work gets done often by people that are evaluating our models. So there's quite a lot to it, and I don't want to take the rest of the time, but that would be my initial answer.
Julia, do you want to go next?
Yeah, I think it is quite a hard question to answer about how to, how to actually show that these models are doing a good job when I think, one of the questions they want to answer is what's the 200-year return period? And we can't really verify that unless we wait 200 years. But I think obviously, as Alex said, you verify on the data that you have at the moment. I think having a range of models and different techniques is a good thing, because if you find one method is predicting something very different to other methods, then you can know, at least you're aware of the huge uncertainty. Whereas if they're tending all to converge, then you might have more confidence in what they're saying. But yeah, I also think maybe some perhaps this is done in the insurance industry, but real-time verification, perhaps, as events happen, compare them to your event set. But yeah, I think it's tough to prove when you're looking at such long return periods.
Yeah, definitely. I mean, sort of empirical, it's very hard to empirically invalidate something when you're trying to increase your sample set.
Yeah,
Karen,
and
do you have
that's where I'll just add one thing, which is that I think that's where the shape of the EP curve can be useful, and that's where kind of people will look at that and go, that's where the science comes in and go, has a storm that has occurred in our historical data set, is that kind of the worst that's possible, or can we envisage worse? And that's the whole point of CAT models and these stochastic event sets, right? They're saying, oh, it is possible to get something worse. And if it's a reasonable CAT model, if it's a reasonable approach, then yes, as Julia says, we'll have to wait 200 years to actually see empirical proof, but we have confidence that our CAT model is saying, because it's based in physics, it's based in real statistics, it's doing a good job of saying what the 200-year will be. Hard question to put succinctly, but yeah, hopefully that helps.
Callum, do you have a statistician's
Yeah, I guess I can build on what the other two said. So validation and diagnosis that I think are key for any application, right? The other two have already mentioned that, and that's very obviously important. But there's two other things which I think are also really worth considering. From my perspective or background, making sure that your theoretical assumptions or framework is well-founded, that there are good assumptions going into the data. I think a lot of historical approaches didn't really make realistic assumptions for environmental data. Now we're starting to kind of update some of those assumptions, and we're making sure they actually agree with what we observe in practice. So there's some good theoretical foundation of whatever you're doing. And number two for me is communication. Because I think if you don't communicate the actual model, if you don't communicate what is going on under the hood well enough, people don't have confidence. Right. And I've had the unfortunate experience I've sat through so many talks at conferences where someone's just, within the course of 5 minutes, they've covered 15 or 16 equations, and I'm just not paying attention anymore. I've kind of lost any sort of concentration, because it's you don't really have the capacity to understand that much that quickly. So I think there's a real lack of communication sometimes with these key ideas, and then people don't maybe understand it well enough, and then they don't have confidence in the process. I think it's not just a matter of validating, but also communicating that these ideas are really quite simple if you can explain them with pictures. That's always my perspective anyway. And I think a lot of people think with AI especially that it's this kind of magic box, and if you really look at it, it's just a fancy function, I think. So
yeah, definitely. I mean, I suppose we're in a scientific discipline, but it's also a social discipline, and if you can communicate, you're going to get things across a lot better. Great. I'm going to move on to some of the attendee questions. I suppose we'll start at the top. So this one's for you, Alex. When you say GCMs, you mean the latest CMIP models under different socioeconomic scenarios?
Yeah, I'll try and answer a few of these quickly. So, I mean, sort of general circulation models. So, Julia actually kind of somewhat, had a presentation along similar lines of Primavera. Essentially, what we're doing, right, is we're running a GCM, on history. We use 1979 to present day, and then we're slightly perturbing the initial conditions, and then we're letting chaos do the rest. And you then suddenly, if you do that 2,500 times across 40 years, you've got 100,000 years, which I think answers someone else's question as well in the Q&A. So that's essentially what the GCM is doing. It's CAM4 for those who are interested, as a community atmosphere model. So there'll be some good information on that online if you want to know more. Do you use decadal predictions? As I mentioned, the focus of our work mostly with stochastic event sets is to focus on what the near present climate is now. However, to do that, we need to understand how things might have changed decadally up to present day. So we certainly want to understand those decadal signals, but we don't necessarily do it first thing for our CAT models because they're based in the near present climate. However, we do have climate change based products as well, which then will look more into that. But that's not so much to do with this GCM that I showed and the specific global framework that I presented. So it's kind of another topic.
Great, thank you. Callum, there's one for you about how these methods sort of scale to sort of larger numbers of sites or stations.
Yeah, so I had two comments on that really. So the kind of historical conditional extremes approach, the one I mentioned where you kind of regress on one variable, that extends very readily to however many variables you want. You just pick one conditioning site and then you fit the model pairwise over different sites. So it's really not difficult to apply that approach in a higher dimensional setting. From what I showed, there's no additional steps. You just kind of treat everything pairwise. But for the geometric approach, I showed everything in kind of the two variable case. You can extend these ideas to the higher dimensional case, but you lose the ability to kind of visualize the models, and it becomes a lot trickier to maybe estimate some of these sets and quantities. And that's where we need new methodological innovation. That's where there's a lot of stuff going on with how can we impose in particular notions of sparsity. So if you're kind of fitting a model over a big region and two sites are really far away, you kind of just assume they're going to be independent, right? You don't need to kind of try and model the dependence because they're so far away, they're not going to be correlated. So that's where you need kind of quite clever notions of sparsity, perhaps graphical models or spatial models to account for that. Like I said, there was actually a spatial model that came out this week. So I think it's because it's such a new idea, there's new innovation all the time kind of coming out. And I think within a few years, there'll be or there will be adaptations which allow it to be, applied in a higher dimension setting. For the moment, I think the only thing you can do is kind of focus on smaller regions and then fit the models separately over different spatial domains, for example.
Great, thank you. Just a reminder to keep putting questions in the chat. Julia, I have a question about whether you've got any thoughts about how this sort of method would apply to sort of future climates. I suppose it seems conceptually simple, but I'm sure it's not that simple.
Yeah, I think the original plan when we did the project was to run it for that there were future runs available out to 2050, but what we encountered was that the transfer functions that we used to get from the winds to the gusts, they were fitted in present day, and when it was applied to some of the future data, it was giving values that we just didn't trust. So I think that so I think in theory it's doable. I think you'd have to think about, maybe the next generation of models which are going to be higher resolution, are going to, it'll be, I'll say easier. It'll be obviously very difficult with all the data processing, but that might improve things. But it's in theory it's possible and conceptually simple. It's just this issue of does your bias correction of the present day apply in the future?
Sure. I mean, I always think that question, does our bias correction apply very well to extremes? I think you mentioned that specifically in your talk, but Alex, do you have any thoughts on that? Because we all use bias correction a lot.
Yeah. Yeah, again, in terms of how, it depends exactly what bias correction you're talking about. I think, in terms of like detrending history to understand the present day, again, we're going to be focused on what's the risk over the next 5 years or so. That's what we're designed to do. And when we think about climate change, we're thinking much more from an adjustment perspective. Does this shift the dice? Does this load the dice in a different way? Does this shift things upwards or downwards? So again, this is where that communication thing is so important, that Callum mentioned. Our models hopefully have all that information about exactly how we've done the detrending, and that's up to the users to determine that they are happy with how we've done that. For our models, we have to approach this in different ways depending on the peril. For severe thunderstorm, I think I mentioned in my presentation, the reports going back before the film Twister came out, were much less numerous. Then there's more interest and there's more reports, and there's all these kind of biases, and we can't necessarily separate out all these different effects that are going into these biases, but we can nonetheless statistically detrend them. At the end of the day, it comes down to expert judgment to determine what is the near present, and do I trust the reports that are there now? So again, complex question, but hopefully that gives a few ideas at least to those watching.
Great. I suppose, as you say, it comes back to what Callum says. We've got to be able to communicate these
absolutely
thoughts and what we're up to. Okay, I'm just going to share my screen. I think we can wrap up now. Okay, thank you everyone for joining. I think that's been really great. A massive thank you to our speakers. That was a really great set of talks, I think. If there's any questions, please get in touch. Oh, this is at the beginning, not the end. Oh well, that's fine. Thank you everyone for coming, and if there's any questions, get in touch with me, I suppose, and I can pass them on. Thank you all for joining.